get started. Hello everyone and welcome to our latest Austmine webinar. My name is Sam Takasiris. I'm the Membership Manager WA at Austmine. Before we begin, I'd just like to acknowledge that I'm hosting this webinar from the lands of the Whadjuk Noongar people. I also acknowledge the traditional custodians of the various lands on which we all work today and the Aboriginal and Torres Strait Islander people that may be attending this webinar. I'm joined today by Michael Zolotov, the co-founder and CTO of Razorlabs. Michael will talk about the top misconceptions that prevent predictive maintenance initiatives from being translated into tangible value and share strategies that can transform these initiatives into value drivers for mining companies. Now, as a little bit different format today, as we want this to be an interactive discussion, please submit your questions as we go. So this is a great opportunity to get expert insights on the topic from Michael. He will respond according to those questions. So if you just use the Q&A button at the bottom of the screen to send through your questions anytime. You can also upvote on other audience questions that you most want answered. We will obviously try and get to as many questions as we can in the time that we have. So with that all said, I'd like to now hand over to Michael to commence the discussion.
Thank you very much, Sam, and thank you for hosting me. It's really, I'm really excited to be here in front of everyone. So in this session, we're going to speak about predictive maintenance and how we can realize the full potential of predictive maintenance. Regarding the agenda, my goal is to present for no more than 20 or 25 minutes. As Sam said, feel free to send any questions that you have. I'll try to answer them already during the discussion, but don't worry, after the session, we're going to also have time for Q&A, so we can also have a discussion there. And yeah, let's make it dynamic rather than a monologue. And that's it. Let's go. So in terms of the agenda, after a really brief introduction about myself, I'm going to speak about 3 predictive maintenance misconceptions that many times lead to failure of predictive maintenance programs. We're going to speak about them. We're going to speak about how, from our experience, we recommend to resolve them. We're going to give several pretty cool examples on real-world mining equipment and deployments there. And obviously, we're going to summarize everything to a kind of a cheat sheet on predictive maintenance engineering, I would say. And finally, the Q&A session. But again, feel free to just jump in with questions here in the Q&A section of Zoom. So that's it. Let's begin. So really, a few seconds about myself. I'm Michael Zolotov. I'm the co-founder of CTO of Razorlabs. I'm going to present the company really briefly in the next slide. I founded overall 4 companies. So Razorlabs obviously focuses on the mining sector. We have other artificial intelligence companies focusing on other areas such as financial sector and defense. I have masters in electrical engineering. My first degree was in computer science and physics. I began my career by basically hardcore engineering of sensor fusion for mainly airborne sensors, whether it's optics, whether it's telemetry, radars, and so on. So really being able to fuse together different sources of information, mainly for intelligence purposes. And in the last 7 years, really specializing specifically in mining equipment, understanding the different equipment types, understanding different failure modes, understanding different root causes, really deeply understanding mining equipment. I visited dozens, if not more, if not hundreds of mine sites. And this gave, together with my colleagues and my amazing team in the company, this gave us the expertise of the method to build the methodology that we're going to present. And basically today I travel a lot, whether it's in Canada, US, here in Australia, and so on, to advise multinational corporations regarding a simulation of predictive maintenance technology, artificial intelligence technology in the mining sector, and similar topics. So really one slide about Razorlabs to give you a background, and then we jump straight into the discussion. So Razorlabs is concentrated on predictive maintenance, specifically for the mining sector. It exists for 7 years. We completed many dozens of projects, really a lot of activity. We have 2 offices here in Australia. We're expanding offices in the US towards activity in Canada as well. And obviously the R&D is here in Israel. What gave us an amazing boost was to be chosen among the 100 most promising AI companies in the world, and actually the only one in the category of mining. We're a public company today. We made a really amazing journey from a bootstrap company up to an IPO of $150 million 2 years ago. And that's it. That's what we do. We do predictive maintenance for mining. And mining and metals, I would add, and this is our focus. So framing the problem and then obviously speaking about the solutions. So when I look at the motivation for this webinar and for this discussion, is that when we meet today with miners and with metal companies, we see that they have a lot of experience. They really want predictive maintenance. They understand the benefits of predictive maintenance, both in terms of availability of equipment, both in terms of throughputs, recovery, if it's gold and copper and so on, whether it's safety issues, whether it's ESG, that is today very popular in the corporate offices, but really assimilating and integrating predictive maintenance is really hard. And the different pitfalls along the way cause up to 70%, that's a number that we found, of predictive maintenance programs to fail. And when I mean failure is basically missing the goals that were set as a target for these programs. And in this discussion, we are going to speak about several misconceptions, several, I would even say, myths that we think from our experience is a major reason for this failure. And we're going to tackle them and at least give our experience, from our experience, how we think they can be resolved. So obviously there are many hurdles and many challenges in assimilating predictive maintenance programs, starting from the culture of the miner or industrial company to the team structure and many other considerations. In this specific webinar, we're going to speak more about the engineering part, the technological part, the product size. So this is what we're going to focus on. I think it is also more relevant to the audience here. And what I want to say is just, obviously, these are not the only ones. These are merely the ones that we're going to focus in this webinar. So first of all, we're going to discuss about what is the difference between big data, which is really a buzzword in the last, I would say, decade, versus the right data that we need to actually perform predictive maintenance. We will then discuss what is the difference between predictive maintenance and prediction of failures versus prescriptive or prescribing actions, why this difference is really critical, and why it is actually a critical part of making predictive maintenance programs work. And lastly, we're going to speak about sensor deployment. Sensor deployment is today a very hot trend. We see many companies do it. And we're going to ask ourselves, okay, is it enough? And if not, what is actually needed in addition or as a part of sensor deployment in order to actually maximize our chances of success here. So the structure of the webinar is we're going to go one by one. We're going to present the issue from our experience. We're going to recommend how it can be resolved. And we'll just take it from there to the summary and discussion. So let's start with the first myth. So the first myth speaks about big data versus right data. And the myth is basically as following, right? The myth says that the big data that miners and industrial corporations already collected so far can be easily leveraged for predictive maintenance. Basically, the concept is if I just take the existing data that I have, I can basically successfully predict failures and assimilate a predictive maintenance methodology within the corporation. The reality, and obviously we're going to give more details about it, is that the existing data in most of the mining corporations, obviously I'm simplifying and generalizing here by definition, but it is mainly based on PLC tags stored in the historian. And what we're going to see is that while it is big data, right, hundreds of gigabytes, maybe even terabytes of data, depending on the size of the company, many times it will not be the right data for an actual successful predictive maintenance implementation within the company. So now let's dive one level deeper to speak about what is the reason for that, and at least what are our thoughts about that. So let's break down the existing big data that miners have today. Okay, well, what is it actually composed of? So here we see the pyramid of automation. I guess you're very familiar here starting from the sensors through the PLC scale and up to the ERP. When we look today at the approach of many of the companies in this field, they will just use the existing data, and the existing data will have inputs such as mainly the historian. So what is the historian? It will have, for example, temperatures, calculated variables of the PLC. It will have different commands, modes of operations of the machine, obviously sensors there in the field, alarms, and so on. Okay, so these would be the inputs that the system will be looking at. And the outputs or the target variables will be mostly either stoppages, such as what is recorded in the MES, delay counting system, every organization calls it otherwise, or maintenance work, such as what we have in SAP or other ERPs that are used. So if we really break down what is the data that mostly exists today in miners, it would be mainly historian as an input and stoppages or maintenance work as an output. Okay, obviously, simplicity of this webinar. Now, if we take one step ahead and we ask ourselves, if I went to a condition monitoring expert that has 30 years of experience doing specifically condition monitoring, predictive maintenance, reliability, condition-based maintenance for the equipment, and I would just ask this expert what he or she will look at when performing their job, they would actually give a very different answer from what we just saw in the previous slide. So I would say roughly prioritizing it, number one would be vibration data, right? Every expert would say that that is the bread and butter of condition monitoring. Vibration data is critical to be able to predict and monitor the condition of basically almost any rotating equipment, from a motor, a pump, a gearbox, bearings, and so on. And they would say that almost all failure modes in these equipment pieces would be seen in vibration data. And we already see here a gap that's forming because in most times, vibration data is not a part of the historian. This is actually pretty rare to see vibration data stored in the historian. It's not something that is frequent. In addition to vibration data, they will add oil analysis, right? So oil analysis, such as the elements in the oil, humidity of the oil, and different parameters of the oil, gives us a pretty good indication of contaminants of the lubrication, debris that are caused specifically because of wear and tear of the equipment, which is exactly what we're trying to detect. In addition to oil analysis, they will look at thermography. So thermography gives us a pretty good indication of overload, of overheating of components, and different electrical root causes of electrical failures. And yeah, they will look sometimes at historian or SCADA system, basically what we call telemetry of the machines, but they will mostly use it for root cause analysis of the failures that they have found using the other methods here, the other data sources here. And the analogy that I like to use, okay, that's an analogy I got from an expert in this field, is that basically relying solely on the historian to perform condition monitoring is basically like in asking a doctor to diagnose a patient based on the Apple Watch, right? So the Apple Watch will give you some telemetry, right? It can give you your heartbeat. It can give you maybe different angles and so on, maybe your speed and so on, but it will never give you profound data such as what you get in blood work or what you get in CT scans or X-rays and so on. And my analogy is that these data sources are the ones that are many times missed by the predictive maintenance program. So I guess that my message here is that if we want to maximize the chances of success of predictive maintenance programs, we need to use the best practice data today for what experts are using for condition monitoring, right? So we spoke about vibration data, oil analysis, thermography, and yeah, historian as well, but it cannot be an only source. Okay, so that was myth number one. Myth number two is, let's speak about prediction. So myth number two says, models that predict failures give enough value. Okay, so many times we see organizations from small startups to huge conglomerates, really focusing hard on being able to predict a failure into the future as precisely as possible. I can say that after dozens, if not more, of meetings with miners, this is only a portion of the story, because most failures, and it is written here, require very diverse actions to actually prevent the downtime, which is what we're looking for. So solely predicting the failure is actually not enough. We're gonna dive a few layers into that in the following slides. And what is actually critical is to prescribe a specific maintenance action to realize the value. Okay, so now let's dive a bit into that to understand why. Okay, so the key word here is actionability. Okay, how actionable are these systems? How easy is to translate the outcomes of these systems to real world actions that are performed by a maintenance superintendent or a maintenance engineer or reliability engineer on the field that don't care about AI, don't care about deep learning, don't care about the technology under the hood. They care about concretely understanding what to do to increase the reliability of the machines and to increase the to avoid downtime and to increase the throughput. So if we look today at what is mainly done today in condition monitoring on sites, most of the times these will be reports from, let's say, 50, 70, 100 pages long. Okay, basically speaking about the condition of the different equipment on site. In the more sophisticated clients or in the more sophisticated miners, we will have them in a digital system rather than paper, but the concept is pretty similar. And eventually, these systems will give what we call symptoms. They will tell you, okay, this specific, for example, motor or bearing in the pulley of the conveyor, as an example, we are detecting wear. Okay, so this will be either in form of an anomaly that is in the system, either in form of a raw here in the report. But the problem is that if I want to actually convert it into an action, when we speak with condition monitoring experts and with reliability experts, what they will tell you, obviously generalizing here and simplifying it a bit for this webinar, is that the root cause will have a tremendous impact on what is actually needs to be done, right? So the same, for example, motor bearing wear or pulley bearing wear, whatever it is, can be caused because of overload, oil contamination, imbalance of the belt or the motor itself, lubrication failure, and so on. And each of them will drive very different actions. And what happens many times is that I have failure on site, or at least an indication of a failure. Okay, I identify the symptoms, which is, for example, the bearing of the pulley that I need to replace. But after I replace the bearing of the pulley, because I didn't really solve the underlying real issue causing it, the new pulley bearing will fail as well. It can happen after 3, 4, 5, 6 months, whatever it is, but I will have this endless loop of failures happening again and again and again. And despite the fact that I'm able to maybe alert about all of them, sometimes, many times it will not be the case, what will happen is that the actual workload on the team will not decrease because they're still chasing all of these replacements over and over again. And just by being able to identify the real root cause of the failure, this is what will allow the team on site to actually break this circle and to really resolve the root cause that will break this loop and prevent not just the next failure from happening, but all the further failures that will happen. We're going to see an example of that in a few slides. So this is a critical thing to understand, right? The myth says predicting failures is enough. Our claim is that it is not, because just predicting the bearing failure, which is today a common practice in almost all condition monitoring platforms, is just not enough, because it will the team will still be required to perform very heavy investigation, which many times they will just not have the resources to do. Okay, and because they will not do it and they will just stick with the symptoms, it will basically not be effective at all, because they will still need to be replacing the equipment over and over again. Okay, we're short of time, so let's move on to the next myth. Let's speak about sensor deployment. So sensor deployment is an important topic to mention because it's a very hot trend today in many miners and metalwork sites. And the reason why it does not automatically resolve predictive maintenance and does not automatically lead to success are two reasons. One reason is, or two reasons that stem from two different categories of sensors. The first category of sensors is sensors that just give you raw data. They will give you, for example, vibration RMS. They will tell you temperature. They will tell you current, whatever it is. And to actually process the raw data requires, if it is not followed by some analysis or some automatic analysis layer, it requires tremendous expertise from the site, but also tremendous time and resources that most sites just cannot put into it because they're short of resources. And what we see in many mine sites is that they have a lot of sensors, but they just don't have the time and expertise to actually analyze them. Second of all, are sensors that do come with built-in analytics, but the problem with these sensors is that they will just analyze their own signal. They will not analyze, they will not combine it with other signals. Now, let's speak a bit about why this is important, and then I will use maybe a different analogy. So let's say we have the same bearing wear in the motor. It can be also other symptoms that we see here there on the mine side. Okay, so what I'm trying to do now is I'm trying to cross out the different root causes in my pursuit for a specific root cause that will allow me to prescribe a specific action to the site team. So now let's say I'm trying to cross out overload. My ability to cross out overload is just will require me both the vibration data that in the first place will indicate about the bearing wear, okay? But in addition, I will need to look at data such as currents, maybe power, maybe temperatures, depending on the use case, to make me understand that this is in fact overload. Okay, so for example, a vibration sensor that just analyzes itself will never be enough to say that it is an overload. So it will never be enough to cross out the this specific root cause. If I'm trying to cross out all contamination, okay, obviously, naturally, I will need to fuse the vibration data with the oil data because the oil data gives me the indication of the oil contamination. I have no way of assessing the oil condition solely on the vibration data alone. It's just it just doesn't make sense. It's undoable. If I'm looking at belt imbalance or motor imbalance, depending on what the use case is, I will actually need to look at CCTV cameras because CCTV cameras give me an indication of the balance of the belt. They give me an indication of the centrality of the ore. We're going to see it in the next slide. And this is actually critical to be able to cross out this indication. And by fusing it together with the telemetry, such as the tension values, speedometer of the belt, and obviously vibration data, this is actually crucial to cross out this root cause. And finally, if we get, for example, for lubrication failure, similarly here, I will need to look at telemetry. I will need to look at the status of the pump, at the cycles, whether completing, not completing, maybe pressures, maybe flows, depending on the use case. What I'm saying here is that combining all the data together, as you see here, is just an example, but it really generalizes well to any other mining equipment and any other failure modes and root causes. Is critical. Combining everything is critical in order to get to this final, okay, this is the root cause, this is what we prescribed you to do. So this is critical. It is very resembling a doctor, right, that will always look at your blood works together with the X-ray, together with the CT, and the combination of them will allow the doctor to say, okay, this is the underlying issue that the patient has, and this is what needs to be done in order to not just treat the headache, which is the symptom, but the underlying real issue that will resolve the problem altogether. So very similarly in machines. Okay, here we see an example of how it looks like in real life. So the use case here is actually pretty interesting. That's a use case of a worn pulley. Now, why am I displaying you a camera? Because when the pulley is worn, one of the reasons why a pulley can be worn is that the belt is imbalanced. If an imbalanced belt is get unnoticed for weeks, it will actually cause the pulley to be worn out because of the imbalanced load on the pulley. And once you have a camera, and many times sites already have cameras, and if not, it's super easy to install one, you're able to basically automatically extract both the alignment of the oar on the belt and the alignment of the belt on top of the conveyor itself, so that if there is an imbalance of the belt, not only you can indicate it to the site, but you can actually associate it with the vibration data coming from the pulley. So just like the doctor, I have vibration data coming from the pulley. I have the CCTV camera here looking at the different parameters of the belt, and imagine how many parameters I can extract. It's the centrality of the oar, the centrality of the belt, oar characteristics, tons of other materials. Imagine that this is also combined with the tension values, the weightometer values, ambient temperature that has also an impact on the tension values of the belt as well. And once I look at everything holistically, then I'm able not just to give an anomaly or to give an alert, but I'm able to actually find the specific root cause, to give a specific instruction to the team on site that will perform a very simple action. By the way, I mean, balancing a belt should not take more than half an hour, 45 minutes, but it will actually prevent all the further replacements of that pulley bearing in the future, which is a really cardinal effect in terms of availability, workload on the team on site, and so on. So this is essentially what we do. We've built a product that's called DataMind. The product includes hardware. The reason why it includes hardware is that, as we discussed, it is critical to have all the critical data that condition monitoring experts use today in order to really give a holistic condition monitoring and predictive maintenance solution. It means that if there are no vibration sensors, and these are critical, we will install them. It means that if they don't have the right telemetry, such as currents, temperatures, voltages, powers, and so on, these can be installed. Obviously, cameras, the way that we saw, and this allows us to get the raw data, which is critical for the analysis. The analysis itself then goes on and combines all of these different data sources together, just like a doctor does with patients. And basically, these are all combined to give you, and this is the critical part, to give the miner the exact root cause that is causing all these symptoms. So the goal is not to just prevent the upcoming failure, but to be able to prevent all the further failures that might have happened in the future if the root cause is not dealt with. And by definition, the combination of these data together not only requires domain experts to be able to build this system, but the support of the domain experts is actually critical to answer any questions and needs and concerns of the site. This is a critical part of what we do. So that's it. I want to just summarize with key takeaways, like a kind of a cheat sheet from our experience to predictive maintenance product engineering. So one, as we discussed, leverage the best practice condition monitoring data. This is critical part, because if we just focus on one source, such as the historian, which is done many times, it is just not enough in order to really capture the breadth of the failures and to capture the real root cause, which makes them actionable. Small data requires domain expertise. We just discussed it. So big data, these are the terabytes of data, as we said, are many times just not the right data. When we focus on what is actually needed, so the vibration data, oil analysis, cameras, and the parts of telemetry that are critical, we see that actually data becomes much smaller. And in addition, because critical failures are sometimes very rare, I guess that you also know it from your expertise, there aren't actually thousands of examples to train machine learning models on. So this requires to combine domain expertise into the systems, which will allow the system not to need these thousands of examples, which are just many times unavailable. Failure prediction and anomaly detection are not enough, because we want to provide a specific action that for mine site team will be very simple to understand, very specific in what to do in order to prevent the downtime and all the further occurrences. Prescribing specific maintenance actions is essential for effective maintenance. We just discussed it. Failure root cause analysis is essential to increase equipment reliability. As we said, just predicting failures will not really increase or will not be as effective in increasing equipment reliability because it will just prevent the symptom, but all the further failures will just keep on occurring and the overall reliability will stay roughly the same. Our goal is to obviously increase the equipment reliability, reduce the workload on the site teams. It is very critical, and therefore the failure root cause analysis is a critical part of that. And finally, sensor fusion is essential for failure root cause analysis. So you kind of see this logical flow of, okay, if I want to get to actionability, very specific actions, I need to prescribe specific actions. For that, I need failure root cause analysis. For that, I need a sensor fusion. So this is a kind of our logical methodology when we built and engineered our product around it. And I guess that this is it. This is my email address. Also, after this session, I'll be happy to follow up with any of you regarding any follow-ups that you might want to make. I think I will be happy now to also answer questions here in the Q&A section. Okay, so let's open it. Okay, so I have here a really good question. Do you need all data sources to be available at the start? Okay, so this is a really good question, and the answer is no. I maybe want to start my answer from the business perspective. Let's maybe jump to the relevant slide. Okay, so from the business perspective, actually, demanding the client to have all of these data sources together is a very hard demand that will really reduce the scalability of any solution. It means that the models, and this is not an easy thing to do, need to be able to handle missing data. So the analogy that I think is a good analogy here is that when you come to a doctor, obviously the doctor can tell you something based on blood works alone, and in my analogy, blood works is vibration data. They might not be as sure of their diagnosis. They might prescribe additional tests, but they will have a direction. Okay, so it's very much the same with at least the models that we've built. We require the bare minimum of vibration data, which allows us to give an indication. It will not have all the root causes naturally, because that's why all the other data sources are needed. It might not be with 100% of confidence, but with 90% or 80%, depending on the use case. But it makes the deployment process gradual, and this is a critical part. It allows the client to see value along the way and not needing to jump from 0 to 100. Okay, I have here another question that's a rather long one, so let's read it. Are you suggesting that all components can be continuously repaired? It's my understanding that every component actually has a life, and the goal is for that component to last that life, many thousands of hours, and then that allows for planned component changeout. Something the best solution is to scrap the component, replace it with new. Okay, so let's answer the question. Let's break it down to several layers. You are correct that when a component comes out of the factory and it's completely new, according to the spec, it should last some X number of hours, 10,000, 20,000, 5,000, depending on the component. But what happens in real life is that this component might either experience out of spec environment, either the environment is too hot, or either the load is much higher than anticipated. We had, for example, an example of slurry pumps and one client that the slurry was just completely incompatible with the pump itself. So different environmental conditions from the operation itself, from the environment and so on, they might drastically reduce the life of the component. And this is why the continuous, as you said, the continuous condition monitoring is so critical, because instead of lasting 20,000 hours, some components might just last a quarter of that or even less, and some components might last more. So the name of the game here is to be able to find in advance failures before they happen and the root causes, so that Once is you just perform maintenance when it is needed, and on the other hand, you do not perform maintenance when it is not needed. Both of these together basically reduce the workload on the site team, and in addition, obviously contribute to the availability of the equipment, the throughput or recovery on sites, and so on. So, correct. The components can be, from our experience, and we saw it in dozens of sites, it can be continuously repaired. The question is exactly what needs to be done and precisely when in order to maximize this overall function. How do I do it just in time? So on one hand, I don't have failures, but on the other hand, I don't over-maintain because that's just increased workload, increased resources from the site team. I hope that it answered your question, Ross. Otherwise, feel free to. Okay, so there is here another question. How much historical data do you need? So that's actually a really good question. And obviously, I can answer for Razorlabs. I cannot answer for other companies. We work today in many countries, and while some countries are very advanced, such as Australia, most mine sites have some instrumentation already. They have a historian in most cases with some history and so on. Other countries, such as countries in South America, whether it's Chile, Peru, Brazil, in many cases, it is not infrequent. I mean, it is pretty frequent to come to a mine site and they have no sensors whatsoever. They have no instrumentation whatsoever. And that demanded from us to be able to deploy models without needing any historical data. So I can say for Razorlabs, we do not require any historical data. In the same sentence, I will say that if it exists, obviously it helps. Just like if you have a medical history and you come to a doctor, it will help the doctor to have a better intuition, but still the doctor will be able to diagnose you without any historical information. The way that we did it is that we took domain experts, we took mining domain experts, mining condition monitoring, I would say domain experts, people with 20, 25, 30 years of experience. And together with them, we understood what are the features that they are looking at when they are finding failures, when they are looking for root causes and so on. And because this information, this knowledge of 30 years and hundreds of mindsets that they have seen is already within the system, it just works out of the box. I mean, we deploy it. It uses all this preliminary knowledge just like a doctor does. So it does not require any historical data. Having said that, having the historical data just helps to be more sure of the diagnosis that is being performed, just like with human doctors. But it's a really good question. Any other questions, friends?
Yeah, Michael, I'll go if no one else will at this point. Can you just run through how does Razorlabs approach a new client? What is your methodology?
Okay, so thank you, Sam, for the question. It's a really good question. And I think it also connects to the question that was previously asked about all the data sources to be available. So I think that the name of the game here is simplicity. Many times we see that predictive maintenance programs fail because it is just too cumbersome for the mine site to be able to set them up and to be able to calibrate them. We see products that after being deployed demand calibration for half a year, even a year and more from the mine site, and having the team on site, the site team, the customer, and having them the actual user of the system and giving them their workload, this is something that it just doesn't make sense, right? It needs to be as simple and as quick as possible. So the way that we approach a new client is as follows. First of all, we come to a site survey in order to assess the overall instrumentation of the site, right? So what already exists there, because our methodology is that whatever exists, we can leverage it. Second thing is that in any gaps that exist in terms of instrumentation, in terms of sensors, we come and we deploy sensors, right? We come and we deploy sensors that allow the data sources that you see here. And this what allows the combination of them to give a root cause analysis and the prescriptive action. So the way it goes is come to a site survey, we assess, takes a few hours, the condition of the site. We deploy any sensors that are needed, and literally a day after the deployment takes a day or 2 or 3, depending on how many sensors need to be deployed. It's very easy. That's it. The system is deployed, and the team on site just sees all the results. All the preliminary knowledge of the system is used, so we do not require any training, fine-tuning, calibration, whatever other players call it. And that's basically it. They see all of the equipment, they see all the failure modes, they see all the root cause analysis of the equipment, and they just see the bottom lines of what needs to be done in order to, in order to prevent the downtime, increase the reliability of the system, of the equipment on site, and so on. Okay, perfect. I guess there are no further questions. So maybe I'll jump to the final slide. So if you remember, okay, see, there's another question. Does the suite of sensors change over time based on the feedback? An oil sample may indicate an issue that demands further testing. So that's a tremendous question. The answer is obviously yes. We didn't discuss it. It is quite, I would say, a more advanced discussion, but we can maybe touch it a bit. So there is a trade-off between the amount of sensors and the granularity of the root cause analysis that can be performed. You're right, we gave the analogy of doctors, it's really the same. So what many times happens is that you start with a kind of an MVP, right? That's called a minimum viable product, right? So many times the client will not start with, okay, let's deploy 1 million sensors. They will say, okay, let's start with some group. Let's get to the 80-20, right, the Pareto. And then we can proceed from there, right? So what happens is that in the beginning, we might deploy some group of sensors. And once the client sees that it's working, then we can go ahead and deploy additional sensors that will make the root cause analysis more granular, that will make the prescriptive actions more granular, and so on. So it's more of an iterative process. And it is critical, as I said earlier, to make sure that the client sees value early on, really quickly. We don't want it to make not only a year, we don't even want it to be a month, right? We want it to be really a few days, that's it. A few days to deploy the sensors, a day after it works, that's it. And then it should be gradual advance or progress from there, while in every step of the way, the client actually sees the value increasing and so on. You are correct, Ross, that in specific cases, we had this before, that once we see that once there is a specific equipment that is super critical to the client, where the root cause specificity is very critical, and we see there is a specific root cause that surfaces, the client might ask, or we can recommend, that additional sensors to be deployed to make sure that the root cause there is more granular. So you gave the example of oil. So oil is one example. It can be other examples can be overload. Other examples can be cameras, right? Many times the client finds out that actually ore anomalies, whether it's too large top size, whether it's the type of the ore, other characteristics, and so on, they actually perform like a domino effect that wears out the equipment. So once we understood that this is the direction, we can actually increase the amount of cameras on site on key places to make sure that it is actually monitored better in the future. So cameras are another example, and so on. So your question is really fantastic. So you spoke about oil, but it can be actually any other sensor as well.
Sorry, Michael, just one more from me. Can you just, from your experience, I guess, run through the difference between different countries in terms of readiness?
Okay, so basically we touched it. I would say that, and I travel a lot, whether it's to North America, Australia, Europe, and South America, and other, Middle East and so on. I would say that naturally Western countries will have, on average, more instrumentation, more historical data available. I would say more sophisticated maintenance programs and so on. And one of the things that drove us to build such a simple product is for it not to just work in Australia, but also work in more challenging territories, whether it's in Africa, whether it's in Chile or Peru or Brazil and so on. And this is what drove the construction of models that don't require historical data or calibration after the deployment, because these territories are just, it will just not work for them. It will just not make sense to deploy there if it's not that simple. Thank you for that question. Okay, so I guess that we're coming here towards the finish. So first of all, again, this is my email address. Feel free to drop me any email with any further questions that you want, any follow-ups that you might want. Thank you for having me here. It was really an honor to speak in front of so many people. And I hope that I was able to share some of our expertise and some of our experience in this field. And looking forward to following up with as many of you as we can. And thank you again for everything. Thank you. And thank you, Austmine, for leading this.
Great. Thank you, Michael. Extremely invaluable insights there for the audience. So big thank you for your time today. Your insights are appreciated as always. Thank you to everyone who's attended, and we look forward to welcoming you to the next Austmine seminar.
Thank you, Sam. Thank you, Harry. Really appreciate it.